Coulomb's law is a fundamental principle in physics, describing the electrostatic interaction between electrically charged objects. It quantifies the force of attraction or repulsion between two-point charges, which are objects significantly smaller than the distance separating them. The electrostatic force can be attractive, pulling opposite charges together, or repulsive, pushing like charges apart. The magnitude of this force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Here, F is the force magnitude, K is Coulomb's constant, Q1 and Q2 are the charge magnitudes, and R is the distance. Coulomb's constant, K, is approximately 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. Since force is a vector quantity, it possesses both magnitude and direction, which is crucial for a complete understanding. Using vectors, we write the force on charge 1 due to charge 2 as F12 equals K times Q1 times Q2 divided by our 12 squared times our underscore hat underscore 12. Here, our underscore hat underscore 12 is the unit vector pointing from charge 2 toward charge 1, defining the direction of the force. The algebraic sign of the product Q1 times Q2 automatically handles whether the force is attractive or repulsive. Let's apply this knowledge to a worked example involving opposite charges, which will result in an attractive force. Find the force between Q1 equals plus 3.0 microcoulombs and Q2 equals minus 2.0 microcoulombs, separated by our equals 5.0 centimeters. First, we convert these values to standard SI units for consistent calculations. Then, we use Coulomb's formula, substituting our converted values into the equation. The calculation proceeds by multiplying the charges, dividing by the squared distance, and then multiplying by Coulomb's constant. After performing the arithmetic, the magnitude of the force is found to be 21.576 newtons. Because the charges are opposite, one positive and one negative, the direction of this force is attractive. Now, let's examine a second worked example, this time with like charges, which will demonstrate a repulsive force. Find the force between Q1 equals plus 5.0 microcoulombs and Q2 equals plus 5.0 microcoulombs, separated by our equals 10.0 centimeters. Again, we begin by converting our given values into their respective SI units. Next, we apply Coulomb's law, inserting the converted charge and distance values into the formula. The calculation involves multiplying the charges, dividing by the squared distance, and then multiplying by Coulomb's constant. Upon completing the arithmetic, the magnitude of the force is calculated to be 22.475 newtons. Since both charges have the same positive sign, the direction of the force between them is repulsive. These examples illustrate how Coulomb's law, in both its scalar and vector forms, allows us to precisely calculate electrostatic forces. Understanding these principles is fundamental to studying electromagnetism and its vast applications in physics.